begin with the word prayer. Dear Father, we thank you for this day, and I thank you for these students. Just ask you to bless this class, Lord. In my prayer. So as I was continuing my story, my friend Crazy Paul and I were in the Rise of Modern Science class, and I forget what we were talking. At the start of the class, we were talking about, what is history, what is science. Actually, we never really asked the question, what is science, which is kind of shocking. It would be some sort of at least vain attempt at a definition of science in such a class, but there was not. Not that you can define that sort of thing anyway. But the point of that is to have that discussion. But anyway, at some point, I forget exactly what it was, but as is often the case, Crazy Paul's argument came back to Tesla, because Tesla looms large in the mythology of Paul. And so he said something about Tesla, and then the professor said, well, I'd like to respond to what you said, but I don't know who this Tesla is. To this, Paul's response was, he threw his pen. He's like, don't know Tesla. How dare you? You're a professor. Oh, thanks. Did I get you? Did I hit you?
No, you're a few inches away.
You are someone teaching a class in the rise of modern science. You don't know who Nikola Tesla is. Get out. Get out. So it was. He invented the Tesla.
I was going to ask if Crazy Paul drives a Tesla.
That is a fantastic question. Does Crazy Paul drive a Tesla? And I think the answer to that is no, but he should.
Yeah. What does he do for a living now? Do you know?
What is he? You know what he does for a living. You are trying to keep me
No,
from
I don't.
You don't. How
do you spend your weekends?
He's a border guard, sleeping.
Wait, really? He can't.
How do you sleep on your side? Stomach, whatever?
What? Yes, clearly. Double major in math and physics, and then he went to Navy Nuclear School, 2 years, passed through. Ended up then selling insurance, I think, for 2 years, something like that. And then got tired of that. Started selling mortgages. Was doing really well, and then 2008 happened.
Huh.
And then he started applying to be a border guard, and then he got that about the same time I started working here. He's been a border guard since about, I think, 2008, something like that. Yeah. He should get a Tesla. That would be awesome. Yeah. I still talk to Paul often. He's one of my best friends. All right. So here we go. Let S be. Okay. So oh man. Now I'm gonna have to go 3 minutes over. So. This is the definition of linear independence. This is not the definition I stated. What's my what? My microphone. Oh. That whole conversation was distant. Probably still came through. Thanks, guys. I'm just standing there randomly throwing a pen. It's good.
Dr. Cook, I think your best video is the one in Calc 2, Fall 17.
Uh-huh.
Fight.
Oh, yes. I bring my kids and there's a marker fight, yeah. Marker fight's a good day. All right, so...
That's how I sold you to all my friends, by the way. Marker fight video.
So I have been letting them down ever since. This is the last time I had a marker fight. But okay, so because apparently my children don't need more encouragement to be rambunctious. So this is the definition of linear independence. This is not what I stated as the definition last time, right? So last time I said this thing about if you set it equal to 0, it implies all the coefficients are 0, right? So what gives? Well, what gives is that definition is equivalent to this one. So what's on the board is the sort of just natural, what you'd expect definition. It's linearly dependent. A set is linearly dependent if one of the vectors in the set can be written as a linear combination of the other vectors in the set. All right, that defines linearly dependent. And if it's not linearly dependent, then it's linearly independent. All right. So the theorem is this, or proposition, I forget anyway. But S linearly independent if and only if a sum of Ci Si equals to 0 implies Ci equals to 0 for all I for any collection S1, S2, Sk in S. So if any finite linear combination of the vectors in S set equal to 0 implies that the coefficients are all 0, that is an equivalent characterization of this linear dependence, right? So I'm claiming that this is if and only if. We should actually go through the proof of that. This is the place, the class where that should happen. So let's go with the forward direction of the proof, right? So suppose S is linearly independent, all right? Or Li, as I often write. And then consider, the negation, right? I mean, consider the possibility that there exists a non-trivial combination. Say that you can write in a V equals to C1 S1 plus C2 S2 plus plus CK SK, where V and all the S's are in the set that's being studied, the set S. And what? What do I mean non-trivial linear combination? What's that say? Right. Oh, and I'm sorry. What am I doing? This is good grief. I should be setting this equal to what? 0 equal to that, and there's no V. Excuse me. I'm sorry. All this talk of select convo just got me so excited I lost my train of thought. So we have this 0 equal to this linear combination of vectors, like so. Non-trivial combination. What's that mean? Well, no. Sum, right, of C1, C2, CK are non-zero. Right? If it's not the trivial combination, there has to be at least one coefficient which is non-zero. Let's say that the jth one is. Suppose Cj is not equal to 0 for some particular constant, right? Then we have that 0 is equal to C1 over Cj S1 plus C2 over Cj S2 plus plus Sj over Cj, Cj Sj over Cj plus plus Ck over Cj Sk equal to 0. Hence, we find that Sj is equal to minus C1 over Cj S1 minus C2 over Cj S2, and so forth, until we get to the last one. What question? Something I wrote unclear? I'm sorry. My font size too small. It's catching up. There's 2 zeros. Yep. Fine. There. This changes nothing. Anyway, the point of this is that you could solve for Sj as a linear combination of what? The other vectors, right? What is that? This is a linear dependence in S, right? Thus, S is not linearly independent. So what does that say about the possibility of a non-trivial linear combination set equal to 0? It says it is not possible, right? That contradicts the given assumption that S is linearly independent. Therefore, this thing I'll underline in red here is impossible, right? And if this is impossible, if star is impossible, so if we have any sum, I equals 1 to k, of CISI equals to 0, that implies that C1 equal to 0, C2 equal to 0, and so forth and so on down the line. So that's the forward implication of this theorem. What if we go the other way? Let's see, what would the other direction be? What should we assume? Assume that whenever we have a sum I equals 1 to k of CISI equal to 0, that implies that C1 equal to 0, and so forth on down the line. Clutter. Better. Now what do we need to prove? Yep. We'd like to prove that S is linearly independent, right? How would we do that now? So we're stuck with definition 4.3.1 at the moment, right?
If we want to show that S is linearly dependent, then, or linearly independent, then we have to show that CI equals 0 for all I.
No, that's what we're assuming. Oh, you have already learned the definition from last class. Very good. But you have to divorce yourself from that for a second. The definition is up here. This is the definition of linearly independent. I am merely assuming that S has this property, that whenever we put a linear combination equal to 0, it implies coefficients are all 0. So I'm trying to take this and prove that S is linearly independent. In other words, that S is not linearly dependent, right? So if I want to do a proof by contradiction, which is what I want to do here, I'm going to say, okay, so suppose S is linearly dependent towards a contradiction, okay? This is a proof by contradiction here. So if it was linearly dependent, if S was linearly dependent, what would that mean? That would mean that there exists V in S such that what? Such that V is equal to something like B1 S1 plus B2 S2 plus plus BK SK, right? For some, B sub I in the field and S sub I in the set, right? In other words, linear dependence in the sense that we can write one as linear combination of the other. Now we're looking for a contradiction to the assumed criteria at the top. So what do we do? So there's something also that should be stated here. What do we know about V as it relates to the S1 through SK? I mean, it's not one of them, right? That's assumed here. That was this word right here, other vectors in S. Anyway, what you do is just do this. So that's B1 S1 plus B2 S2 plus plus BK SK minus V equal to 0, right? But that minus V we could write as plus minus 1 times v, right? And so there we have a linear combination of vectors in S, which is set equal to 0. Are all the coefficients 0? No, right? So here, this is a non-zero coefficient. So we have a linear combination with at least one non-zero coefficient, so that violates the assumption here about S. That's a contradiction. Thus, S is linearly independent. Because supposing it was linearly dependent led to a contradiction, so it must not be linearly dependent, it must be linearly independent. And there you go, that's both directions. Now, so we have this to work with. We can either define linear independence in terms of the statement that you can't write one vector as a linear combination of the others, right? Or we can view linear independence as the statement that whenever you take a linear combination of the vectors in the set, a finite linear combination of the vectors in the set equal to 0, it implies all the coefficients are 0. Calculationally, it's definitely nicer to work with this one, right? This is a calculation. This is a concept. The calculation for problems is often more useful. And that's why, by default, I will state the definition as this. If left to my own devices, if I forget what I wrote in my notes, I will sometimes give the definitions. The other good reason for perhaps giving this as the definition is that this is still the definition of linear independence if you're not working over a field. Right? Only in a field can we do this division business. We lose that if we're working over a ring. But going forward, I'm not saying you have to cite this theorem going forward. What I'm saying is that we will interchangeably use either one of these as the definition in this class, all right? So that's all. So I had to get that off my... I felt guilty for not stating the definition properly and then going through this last time. But then again, I think you probably appreciate me doing what I did last time for the purpose of making the homework more understandable, right? Okay, so moving on. There's another theorem I should state for you. So this is the column correspondence property. Let A be a m by n matrix over a field, all right? And suppose there exist C1, C2, dot, 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 dot. How many, I mean, I'll be greedy. I'll take as many, how many columns are there in A? N. So let's say Cn. So suppose you got constants in the field such that the sum I equals 1 to n of Ci times column I of A is equal to 0. So what is this? This is some sort of linear dependence amongst the columns of A. Well, is it a linear dependence amongst the columns of A? That depends on what? For this to be a linear dependence amongst the columns of A, what do I need to know about the constants? there has to be at least one non-zero constant for this to be an honest-to-goodness linear dependence. Otherwise, it's just a trivial combination, which doesn't say anything about the possible linear independence or dependence of the columns of A. But suppose you have this equal to 0, then, I could put it up here, then the sum I equals 1 to n of C sub I times column I of the reduced row echelon form of A is also equal to 0. But let's not even do that. Let's say the column I of Ri, well, excuse me, I'll get with it eventually, guys. Oh, fine, I don't have room for anything else. Let's just say R, it doesn't have to be I, just R, just like R is equal to 0. And what do I mean by R? Where R is row equivalent to A. This terminology I just used, row equivalent to A. All right, if I had been doing a better job on the last few lectures, I would have wove this into the discussion. Dr. Smith wanted to talk to you guys about the fact that there's an equivalence relation between matrices, where that equivalence relation is defined by whether or not a finite sequence of row operations takes you from one to the other. All right, so you can actually define an equivalence relation from one matrix to another of the same size, whether on the basis of whether or not you can do row operations from get to one to the other. Is that an equivalence relation? Let's just think about that for a second. Let me write anything. Is a matrix equivalent to itself? What row operation can you do? How about just multiply, pick any row you like, multiply by 1. That's a stupid row operation, but it's row operation. So any matrix is equivalent to itself. That's reflexive. How about symmetric? If I go from matrix A to matrix B by row operation, whatever, I can go from matrix B back to matrix A by the opposite of that row operation, right? Because every row operation can be undone, right? There's an inverse to each one. So that's symmetry. And if you think about transitivity, you're going to be able to prove that too. If you can get from row operations from A to B and you can get row operations from B to C, it follows that if you do those row operations subsequently, you can get from A over to C, right? So row reduction is an equivalence relation on the set of matrices of a given size. And if you want to talk about the equivalence classes there, the representative of each equivalence class would be given to you by the reduced row echelon form of a given matrix. So the reduced row echelon form is a unique representative for each equivalence class with respect to this notion of equivalence. Anyway, so row equivalent to A, all that means is that there exists a finite set of elementary matrices such that R is equal to, oh, this marker is worthless. R is equal to, K, EK minus 1, E2, E1A, right? These are all elementary. So we might as well call this whole thing, call the product of, curses. Something's funny. So we could, as we have in the past, label this just E, right? So this is what we know this. If the matrix R is row equivalent to A, then we can multiply by a bunch of elementary matrices and get from one to the other. With that result in hand, this theorem is almost trivial. So here's the proof. In fact, you know what? We can replace this then with a what? Yeah, we can replace this with an if and only if. In other words, this if and only if this. Right. So here's how that goes. So, suppose that we have the sum equals 1 to n of ci column I of A equals to 0. I should warn you, this calculation's sick. So multiply by E. And so we get E times the sum of ci column I of A equal to 0. But by properties of matrix multiplication, I can bring the E in. I can move it past the constant C. And so that gives me that the sum of I equals 1 to n of ci E. coli of A is equal to, I mean, this was E times 0 on the other side, fine, right? But E times 0 is what? 0. But what is E. coli? I mean, this... Don't speak ill of Taco Bell here. How dare you? Have you seen? There's a new Taco Bell commercial, which is amazing. It's like Interstellar or something. I don't know. It's really something. But this is column I of EA, right? By the column by column matrix multiplication rule, which of course is column I of R. And so that gets you that we have the sum I equals 1 to n of ci column I of the row equivalent matrix R equal to 0. It's not bad, right? How can you reverse this argument? What if you go the other way? If you assume that the sum, I equals 1 to n of ci column I of R is equal to 0, then you just, do I need to write anything? Or should we just really observe that we can do what? These are really biconditionals, right? So let me be lazier and just say, okay, so, yeah. Now, this is the so-called column correspondence property. What it says in words is that any linear dependence that can be seen in the columns of A will also be found in the columns of any row equivalent matrix to A. But specifically, what is very nice to look at is the reduced row echelon form, because their linear dependence can be most easily seen. All right, so like example, if I have the reduced row echelon form of V1, V2, V3, V4, is equal to 1, 2, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, and then 3, 7, say, then the column correspondence property says whatever relations I can see over here, let's call this, let me call this R, I need some other letter. Q. Okay, Q1, thank you, Q2, actually very helpful, Q3, Q4. So how are Q3, Q1, how are Q1, 2, 3, and 4 related? Let me start you out. Q4 equals to what? Yeah. That is that not 3E1 plus 7E2? which is what? Of course, that's 3 times Q1 plus 7 times Q3, right? And what about Q2? That's 2 times Q1, right? Claim. We can see non-pivotal columns as linear combos of pivot columns. And also, if you look at it, if you just look at pivot columns, there's no way. Also, the set of pivot columns, pivot columns, the set of pivot columns is linearly independent. Why? Why must the set of pivot columns be linearly independent?
Because they each have a unique solution.
Well, what are the pivot columns in the reduced row echelon form? They're the standard basis, right? They're E1, E2, E3, E4. Are those linearly independent? I mean, essentially by inspection, you can see that those are linearly independent. We could go back to the definition, right? C1E1 plus C2E2 plus da 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 plus CNEN equal to 0 tells you what? So if we take a linear combination of the standard basis equal to 0, it gives us that the C1 through Cn is 0, which is to say that all the C's are 0. So yes, the standard basis is linearly independent. There's no way I can build E1 from E2. There's no way I can build E3 from E1 and E2. These are genuinely different building blocks. So since the pivot columns in the reduced row echelon form are linearly independent, and we know the column correspondence property, it must follow that the original columns in the matrix, which are in the pivot column positions, are also linearly independent. Because to say otherwise would be say that there's a linear dependence amongst the columns, which would then transfer to be a linear dependence amongst E1 through En, which is nonsense. So pivot columns have to be linearly independent. Non-pivot columns, well, that's more complicated. Those will be linearly dependent on the pivots because of the column correspondence property. Does this make sense? I mean, we should look at some examples, right? Let's see here. Let me use my let me cheat a bit here. So this is a very useful thing that I've just shared with you, right? Because you notice what it does? It shortcuts looking at the system of equations. I can see whether or not there's a linear dependence amongst vectors without actually going back to the spanning equations. I just covered it up, but we already found linear dependence amongst the Q's, right? I didn't have to go back and look at the underlying, maybe there would be underlying spanning equations if you wanted to think about it. Let me get up here. Come on, you can do it. So we proved that today. You know, before I even do an example, it's probably good for me. Yeah.
Never mind, I think it's answered in there, but non-pivotal columns are linearly dependent, and pivot columns are linearly independent.
I didn't say that. But the set, I agree with part of what you're saying.
Okay.
The set of pivot columns forms a linearly independent set. All right? The set of non-pivot columns may or may not be linearly independent.
Okay.
But this much we know. Every non-pivot column can be written as a linear combination of the pivots.
Okay.
So if there are non-pivotal columns and we take pivot columns together with non-pivotal, then that will be a linearly dependent set because there's necessarily a linear dependence amongst the non-pivots in terms of the pivots.
Okay.
So this, here's a theorem which is a straightforward consequence of the calculation I was just sharing with you. If we have a set of vectors in Fn, and if we do the reduced echelon form of the matrix form by just gluing them together, if it has less than k pivot columns, then that's a linearly dependent set because that means that there's at least one vector in there which can be written as a linear combination of the others. Right? See, that's why definition 4.3.1 is good to know. Yeah. If, on the other hand, we have k pivot columns, that means that the reduced echelon form of the matrix actually is just E1 through Ek, which is a linearly independent set of vectors, and so by the column correspondence property, so are V1 through Vk. Right? Now I think I'm looking at the question of proving it directly from the, setting the equation equal to 0 perspective, but if you think about proving this from the column correspondence property, it's even easier. Corollary, if you have more than more than n vectors, right? If you're in R3 and you have 4 vectors, if you're in R2 and you have 3 vectors, if you are in Rn and you have n plus 1 or n plus 2 or however any more than n vectors, you're automatically linearly dependent. A set with more vectors than n in Fn will necessarily be linearly dependent because you will have a non-pivotal column when you do the row reduction of the matrix formed from gluing these together. Do you know why we work with Rn? It's because we're close to nursing. That joke was brought to you by Dr. Skambordis. I can't take credit for it. I was like, I guess I'll try it. If we were actually in nursing, it would be even better. We're very close, though, right? I mean, I don't know. All right. Make my missions harder. Let's see here. So here, I'm still doing things like I was doing last class, right? Trying to decide whether or not, well, let's see here. Let's just see if we can appreciate the calculation. I take vectors v1, v2, and v3 as advertised. I do the row reductions. I get to this. So if we believe the column correspondence property, you look at this. You can see that the third column is the sum of the first two. How do I see that? I use my eyes and look at it. That is it. All right, it's by inspection. And of course, the neat thing is when you go back, you can look, oh, look at that. This plus that gives me that. What do you know? That's the column correspondence property. So is v1, v2, v3 linearly dependent? Yes, it is, because v3 is v1 plus v2. Are the non-pivot columns linearly independent? The non-pivot column here is v3. It's the set just containing v3. Any non-zero vector on its lonesome forms a linearly independent set. So taken alone, the third column by its lonesome, that is a linearly independent set. If we also throw in v1 and v2, that's a linearly dependent set. see, linear independence and linear dependence is a set property.
Okay.
So we can't talk about that vector being linearly dependent or
So
that vector.
No, any like one vector is.
Any,
Or, like you can't really say that any one vector is linearly.
if you take one vector and you put it in a set, that set is linearly independent if the vector is non-zero. If it's the 0 vector and you put it in a set, that's a linearly dependent set.
Okay.
What?
Like a dimension or what?
Because if I look at 0 times the vector, I could put 1 times 0 vector and I'd still have 0. So it allows a non-trivial linear combination. Let's see here. Okay, so here's another one. If we take these 4 vectors right here, 1, 2, 3, 4, and we reduce those things, guess what? We're in R5, but whoa. Whoa. So I need to edit my notes here. Just do like a little. Oh, no. I really do want to do it. But I better not. So add a 0, a 0, a 0, and a 0. Make them 5 vectors, and then we'd have this, which would go to that. Which is to show you that these 4 vectors in R5 are actually what? Linearly independent, right? No non-pivots. All right. Here's another one. I have these 3 4-dimensional vectors, all right? I do the row reduction, we get this. So are these linearly dependent or linearly independent? Altogether, V1, V2, V3 are linearly dependent because V3 is what? It is minus V1 plus V2. See, because this third column is minus the first column plus the second column gives me the third column. And the column correspondence property says that any linear dependence in a row equivalent matrix must also appear in the original matrix. This is stupidly faster than what we were doing last class in terms of sorting through the constants, is it not? But you would like to understand what we did last class as well, right? That's why we went through it. It's good to understand what we did last class in terms of actually doing battle with the constituent equations. Like, that's important. However, I will tell you this, not learning this column correspondence property in my undergraduate linear algebra, it did not help me in graduate school. You can get all the way through linear algebra never learning the column correspondence property and just keep solving equations and solving equations and solving equations and you'll get through. But the CCP is very, very helpful. All right, these 4 vectors, if we do the row reductions, what do I do? Oh, I just flippity flopped row 1 and row 3. Which, oh, okay. So and then I did row 1 minus row 2. Anyway, there you go. So hey, why do we like the reduced row echelon form? Hypothetical question. Do we need to get to the reduced row echelon form to answer questions of linear dependence for a given set? Not absolutely, but what's the comfort in the reduced row echelon form is that once we get to that, we know that non-pivotal columns can be written as linear combinations of the pivots. There's no ambiguity. When you're in this middle step, I mean, maybe you can see in this middle step that, oh, look, the first 2, if I add the first 2 together, I get the third, right? So apparently V3 is equal to V1 plus V2. But it's just impossible to miss in the reduced row echelon form, right? So let's see here. This one, these are the non-pivots, so there you go. All right. See if I got another example. So I was cheating. I was using So the whole purpose of that section is to motivate the column correspondence property. I just decided today it'd be more fun to prove it from the start and then exhibit it. As you can see, these notes are still sick. And I think all I do here is basically just go back through those examples that we just went through and emphasize. You can see each one of the results by the CCP. Another thing I should mention, if you want to study linear dependence of the rows of a matrix, what could you do? Right, you take the matrix, you transpose it, it becomes the columns, the rows of the original matrix become columns of the transpose. And then you can use our bag of tricks to study possible linear dependence amongst the columns of the transpose. If you find a linear dependence amongst the columns of the transpose, suppose you find the sum I equals 1 to n of Ci, column I of A transpose, right, equal to 0. Then what do you do to this linear dependence? Take the transpose. What are properties of transpose, among other things? A plus B transpose is? B transpose. You can pull constants out of the transpose, right? And finally, the column of A transpose is equal to the row, the ith row of A transposed. So put those together, when we take the transpose of this linear combination, what do we get? We get the same stupid linear combination amongst the rows of the original matrix. So just taking the transpose of the equation, the column of AI transpose becomes, well, do I have that? I guess technically I would have, I guess, okay, fine, I'd have a transpose here. Yeah, but then what? You could pull the transpose out, right? And then you can just get from that. I'm sorry, I'm not saying anything terribly interesting here at the moment. It's just that if we can find a linear any kind of linear dependence amongst the columns of the transpose will be likewise expressed in terms of the rows of the matrix. For example, if you wanted to find a set of linearly independent rows in the matrix, what could you do? You could take the transpose, find the pivot columns of the transpose. Those would correspond to linearly independent rows in the original matrix. And those linearly independent rows you could build all the other rows from by the column correspondence property, fed through this idea. Here's an example. So I think I took, oh no, this is not that example. I guess I don't have an example of that. I'm sorry, guys. What's this here? Oh, we've already talked about this. If you throw a column of zeros onto the end of a row reduction, it just stays put, right? That excuse me, yowzers, blah. All right, I have wandered into the part I don't want to talk about. See here. Oh, applications. Well, we have a minute left. Good. But in this last section here in Chapter 4, I share with you some applications, among other things. And you've had some of these in the homework already, like you can fit a polynomial that gives us linear equations. Another fun application, if you don't give enough data, you don't get one polynomial, you get a whole family of them. This stochastic matrix thing we'll come back to, maybe not, but there are various other applications of matrices. This is an application to, this is what's called a Markov chain. You start with a little matrix that describes birth and death rates, or something like that. Or what is this? Though this is infected versus non-infective, and it is an interesting example. And So maybe we'll come back to these later. At one point in time, this encryption, you could take the letters 1 through A through Z and call them 1 through 26. Take words, cut them into like little vectors, multiply the vector by the matrix, it would scramble them. Then you can multiply by the inverse matrix to unscramble them. So like this message, when scrambled, this scrambled message, when unscrambled by the inverse matrix, gives you back this, which is like class is canceled. Not true. And then finally, the last example here may be vaguely familiar to you because I asked you in homework. This one. I hope you've looked at my solution to that problem. If you didn't see what was going on as you were doing it, I hope the solution helps you there. The solution to the homework you guys just turned in should be posted sometime today. Maybe, if not already, soon. But anyway, have a good weekend, you guys. Thanks. Next up, determinants. Woohoo!